So welcome everyone to the Applied Algebraic Topology Research Network seminar. The speaker today is Gunnar Carlsson, and the title of his talk is Topological Deep Learning.
All right. Thanks, Sarah, and thanks all you guys for inviting me to speak here. I'm really looking forward to it. I've gotten interested in the last couple of years, the last 2 or 3 years, in the idea of deep learning. Okay, hang on. There we go. And you may not be familiar with it, so I'll give you the very quick run through of what deep learning is. It's a methodology based on neural networks. So neural networks are directed graphs, effectively. It has produced outstanding classification results for complex data types. So there are things out there where you classify images, and you find you can classify, databases of pictures of hand-drawn digits, for example, or cats and dogs, or other kinds of complicated objects. But also, text. There are now very effective mechanical translators or automatic translation tools based on deep learning, and even more complex data types. So one of our own here, Guowei Wei, has, for example, worked on studying molecule structures, complex molecule structures using deep learning. Let's see. So it's a fantastic, almost magical methodology, but there are some problems with it. So the problems are adversarial examples. So for example, it's very important to use deep learning or AI for autonomous vehicles. But here's something that happened to one of these companies not so long ago, which was some of the AI had to be able to read speed limit signs. And so there was a speed limit sign which was for 35, but they had taken that central prong in the 3 and kind of removed a little bit of it. And so what happened then was that the AI read it as an 8 instead of a 3. And that's obviously a problem, right? If you think that the speed limit is 85 instead of 35. So then that's an example of an adversarial example where you're going to mess with the data in such a way that people don't understand, don't see the difference, but the AI fails to detect it. General lack of transparency. It's kind of viewed as a black box, which is a problem in many ways, particularly in some regulated industries like finance and healthcare, where you can't really take black boxes seriously. So it limits the usefulness in those domains. And maybe we'd like to learn more complex models as well. Now, some of that is happening. There's something called representation learning. I won't go into that, but in any event, the general idea of learning more complex models is important. And so what's a neural network? Well, yeah, so it's a network like this where you have neurons and you have edges. And here, this picture, it doesn't quite capture it because most of the neural networks the edges are actually unidirectional, so that there's actually a directed structure to it. And here's an example of a very simple one. So there's an input layer, which is the input data. So each of those neurons here specifies a number. And so that's the input data there, which would be a 3 vector. And then there are some internal layers, which are also neurons, which will be populated with numbers. And the way they get populated with numbers is you assign weights to each of those edges. And then there's a single formula that says that, well, a particular neuron is computed using the formula involving the weights and the values of all the nodes that connect to it. So in this case, these are sort of fully connected layers, if you like. So every node in layer 1 is connected to every node in layer 2, but it is of interest to kind of sparsify those connections. And ultimately the way it then works is you now try to fit this formula that you get at the output there. If you have a formula that you're trying to mimic, or you're trying to get at, or you're trying to build a formula for some outcome that you've got, that you then optimize these weights so that the formula gives you the best possible approximation for this pre-given outcome. So again, this kind of summarizes it here, that the network is trained by optimization algorithms acting on the set of weights. And so you get what is a very large formula determined by the final set of weights. Okay, so now there's a special class of these things, though, as they, as I described them there, those things, can work, but it's very heavy computational load. It's not adapted to anything. It's just, fully connected like that is something that one often uses for small problems at the end of a neural network. But a class of sparsifications, as it's called, so of making sparser networks, is called convolutional neural networks. So the structure of the network is adapted to specific cases. They would be images, in one case, text is another, time series is another. But you could go on here. You could talk about 3D imaging. You could talk about video and so forth. And the idea here is this, that you have each of these rectangles here is an array of pixels for images, say. So we think of them as neurons. And the idea is that they are arranged in a grid. So you actually have a geometry on the pixels, not just a set of pixels. And that geometry dictates how you put in edges. So in this case, what you can see here is that first layer on the far left is your input layer. It's a grid, and then the next layer is a collection of grids, and now you've got weights attached to every pixel in each of those grids in that first layer. But the restriction is that you don't allow any pixel to connect to an arbitrary other pixel, only the ones that are nearby. So as you can see here, if I have a pixel, say in the upper left-hand corner of of that input layer, I would only connect it to something in the upper left-hand corner in each of those grids that you've got there. And so that's kind of a locality condition, as we would call it. It makes the network much sparser. It encodes the condition that we would like. Say, if I have a cat in the upper left-hand corner or a cat in the lower right-hand corner, I'd like to recognize it in exactly the same way. So, actually, sorry, let me stop for a second. I got ahead of myself. What this is saying is, first of all, that we want to study features that are local, features that you don't believe that you have long-range dependencies. There's an additional condition, which is a convolutional condition, which says that for any particular grid in that first layer, then the weights, in the upper left-hand corner are exactly the same as the weights in the lower right-hand corner. It's an invariance condition or a homogeneity condition. And that is the thing that says that, look, you should recognize, a cat in the upper left-hand corner in the same way as you would a cat in the lower right-hand corner. So a question that we tried to answer here, and I'll show you some examples of it. Does learning by these CNNs behave like human learning? We know from neuroscience a fair amount about how people learn to see, and so the question is, does learning by CNNs actually recapitulate that somehow? So this is joint work with my student Rickard Gabrielsen. So what do we want to know? Can we see similarities to what we found in image patch data? And I will tell you what it is that we've found in image patch data from much earlier work in TDA. What happens as the network learns? How does the learning proceed? What are the responsibilities of the various layers? Those are things that one might want to know. So now what I want to do now is tell you and maybe remind you of work that we did on image patches in the early days of TDA back in the 2000s. We studied a data set that come from David Mumford and his group at Brown, 3x3 patches in natural images. Studied only the ones where there's some variation going on, and we didn't include in the analysis the constant patches for pretty clear reasons. They would dominate the statistics if they were in there. It studies only the densest such patches, the most frequently occurring motifs, and we're motivated by the goal of understanding how the tunings of neurons in the visual cortex is affected by statistics of natural images. That was the motivation for the construction of the Mumford set and also for our analysis. And so the findings were these. The first, that there's a high density high variance patches like this. This is using a non-local density measure. And it's pretty clear what this is telling you. This is telling you that linear approximations are really the most commonly occurring things among those things where there's some variance. So in this case, you can see that it's parameterized by a circle because it is basically a discretization of a white to black linear gradient as I move at different angles. So that's maybe not so surprising. What was more surprising is that when we changed the density measure, we found instead that we had this three-circle model came out. So not only was there the primary circle, which is the thing up here, but also the two secondary circles, which instead of, they're in vertical and horizontal directions. And what they do is they transition from an edge or from edges, which are, coming from a dark to a light region, to what I would call ridges, which are, lines, in this case, vertical lines in the left here, in the middle of a white region, white lines in a white ridge in the middle of a black region, and here, similarly in the horizontal direction. Now we found that we could actually, make this even bigger by relaxing the density threshold. And so what we found here is then that there's actually a two-dimensional object which is consistent with this model, and it's our familiar Klein model with the identifications, without a twist in the vertical direction and identifications with a twist in the horizontal direction. And you can see the embedding of the primary circle, which is red, and then the two secondary circles here, which are the yellow and the green. So the Klein model incorporates what happens as I take the secondary circles in all other directions. So, okay, now how does this relate to what happens with humans or mammals? The primary visual cortex is the lowest level processing beyond the retina. Higher levels perform more abstract tasks. The Hubel and Wiesel experiments from some 60 years ago show that individual neurons are tuned to detect both edges and lines or ridges. So this is consistent with the idea of compression of frequently occurring signals, because if you're building a tool to detect something, if you know what happens very frequently, you would want to dedicate a neuron to it. Whereas if something happens much more rarely, you might allow neurons to act in concert. And the visual pathway looks like this. There's the visual cortex, which is fed from the retina. And then you have higher level objects. So V1 captures edges and lines, and then you get more complex objects as I go higher up in the pathways. So let me just say that this Klein model that we discussed, what does that have to do with this? The Klein model is a geometric organization of the sets of edges and lines, if you like, and interpolations between them. So the point is that you don't want to just know that it's edges and lines, but you want to know the geometry on that space, which is something that you can use for computational purposes, as we'll see. Okay. All right. So and now probably for this audience, I don't need to talk about this, but I'm going to be talking about mapper a little bit, and so I'll tell you how usually I motivate this. Normally, I would say, look, the shape of data is important here. Here, this data is naturally approximated by a line, which is linear regression. Here is another data set which is not approximated by a line, but it's approximated by 3 points instead, and that would be called cluster analysis. So we have a shape of a line and the shape of a discrete set of points. You might not think of it as a shape, but it is. And then if we were optimists, we might think we were done at that point, but then we run into a data set like this one, which is better approximated by a loop. We could say we're going to build loop detectors, but maybe we're worried because we don't think we're going to be done then, and we aren't, because a data set like this comes up, and now here's a letter. Well, it's kind of a flared data set or a Y shape. So we don't want to be taking individual shapes, listing them, and building detectors for them, or we'd rather build a methodology that can capture everything at once, that can capture every shape at once, and that would be topological, data analysis, in my view, which is modeling data by simplicial complexes or graphs. So it comes from Euler, and we're probably all familiar with his Königsberg bridge problem that he was asked to do by a benefactor. He found a simplification by a simple network for the problem, removing the complexity of the size of the island, the depths of the river, and so forth. And so, there we go. So here we're going to do the same thing with Mapper. So Mapper proceeds as follows. It takes a projection, one or more projections to a base, to the real line, or and then ultimately then to the plane if I have two projections. I don't actually use coordinate projections. In general, I use more meaningful statistical things. But what I do is I bin the interval or the plane by either overlapping intervals or overlapping boxes. Take the inverse image of those like so, and now apply a clustering scheme to each of those bins, not to the whole data set, but to the bins. So I have now a kind of a soft clustering here, a clustering in which the clusters can overlap. And so I use that information to build in edges for a graph like this. And so at this point, I have reconstructed that circle. Now, this is giving you the most optimistic scenario for this. It doesn't always work this well, but nevertheless, it kind of gives a sense of how one can systematically build these topological models for the complex data sets. And so I'm going to just, in the interest of time here, since I know we want to go kind of short, the point is just that some people might think that it's just about visualization. It is about visualization, but it's also about a lot of functionality that these models have. They're kind of, you can interrogate them in various ways. You can segment them. You can do hotspot analysis by coloring, because each node is a collection of data points. So if I have an interesting property like revenue or survival, I can color by that. And get a kind of a heat map on the graph. And I can explain and justify features or groups. I can do topological feature creation, as we'll talk about here in a bit, and also get model assessment and improvement. So here is now the situation. So this is I'm now getting to the study that Rickard and I did. So this is an analysis of the weight vectors in the convolutional neural network. So in a convolutional neural network, remember what we have. We have each node is connected to only nearby nodes, and we'll say here that it's connected only to the 3x3 rectangle around it, just like we did 3x3 image patches before. And so for each such node, then what I get is I get a 9 vector. I get, in fact, effectively an image patch. It's just that the numbers aren't grayscale values anymore. They are the weight vectors that get constructed in the neural network. And so here's what we found when we did exactly the parallel analysis of these weight spaces on a data set called MNIST, which is you're probably familiar with it. It's a data set of images of hand-drawn digits. And so what you can see here is that it completely recapitulates what we found in the statistics of natural images. This is that primary circle that we found there, and it's appearing here in these weight vectors as well. Now, what you might say is, you might be a skeptic and say, well, you probably cooked up your mapper model, you cooked it up in some way to get what you wanted. And so one way to get around that objection is to say, let's take the data set and let's compute persistent homology of it, just like we did actually back. That was what was done in the statistical analysis of natural images. And so what we find here is, again, that strong signal for the presence of a circle. So this is a way to use persistent homology as a way to kind of verify or validate results that one gets from a mapper analysis. Now, so this was interesting, and I want to emphasize that this is a description of what happens during the learning, during the process of learning. And I'm going to show you this example, which is a little bit anomalous. This is from a data set called CFAR10, which is a collection of objects with 10 classes in it, I think it was. And this is simply a 2-layer neural network. And I want to emphasize that the results that we get here, we believe, are not consistent with what one gets visually, and we'll see in other networks where it is. But I just want to illustrate for you what's happening here. So here's a mapper model, and it's colored by for each node, it's a collection of data points. So I color by the number of members of each node. So, you know, a red colored node has got a lot of points in it. A green colored node has few. And so you can see what's happening in the first layer. This is a 2-layer network. That initially it's kind of very random, but as the learning process starts, it starts to concentrate around the circle, around the boundary circle. And here we actually empty out the middle, and we genuinely get that primary circle. But now what's interesting is now it starts to degrade, okay? You'll notice here it's really circular. Here now it's starting to fill in again, and you're starting to lose some parts of the circle, and it gets even more dramatic as I go here and I go here, and you're finding that what you're actually seeing is you're seeing kind of only the vertical and horizontal directions of the primary circle together with in the middle here something that is probably like a bullseye. So that's kind of strange. What's interesting is what happens in the second layer. Nothing much is happening here. It looks, you know, kind of random. But now as it starts to degrade, you can see that what's happening around the boundary here is getting stronger and stronger. And in fact, what happens is that this second layer compensates for the degrading that's going on in the first layer to give you a primary circle in the second layer. So now, again, this is the organization that I showed you for what happens in the mammalian visual system is different from this. It says that, you know, initially you get the edges and lines and then more complex objects as you get further up. So now here's another analysis of CFAR10. This is a more localized density estimator, looser density thresholding, and in this case we actually recover the 3-circle model in this analysis of the weight spaces there. So this is you know, this is at the end of the learning process, and as I say, it's a different situation from the previous one. And then finally this one, this is a much deeper neural network with 12 layers in it. It's actually got 16 total layers, but these are the convolutional layers. It's called VGG16. And it's trained on a large data set called ImageNet. And what you can see here is that in this case, every single layer has the ability to capture lines, to capture edges. It's got a primary circle in there. But, the first ones have only that. But then over time, you know, or I should say not over time, but as I get deeper and deeper, the responsibilities get heavier and heavier. And I start getting, you know, that secondary circle phenomenon, and as well as bullseyes and lines, bullseyes and crossings, for example, here in number 7. So, okay. So one thing that allowed us to do was to hard code the primary circle and the Klein model, and to give the neural network those as original features in a systematic way. Immediately got a speed up of 2x for MNIST, and 3.5x for a more complicated set of digits called SVHN, which has got house numbers. And also we managed to generalize from MNIST to SVHN better than the standard. So what happens with standard neural nets. So normally if I train on MNIST, the convolutional neural net, and train it to detect or to classify digits from 0 to 9, and I then evaluate that model on SVHN, I actually get 10% accuracy in a 10-way classification problem. So it's effectively random. It means that when you train on MNIST with a standard neural net, you have gotten more, you've trained on, you know, some stuff maybe that isn't what humans would think of when we're classifying the digits, because humans can transfer the learning back and forth without a problem. And what's showing here is that this gets improved to 22%. Now, what we'll show is that you can actually do even better than that. And so I'm going to talk now about TDA and deep architectures. So convolutional neural nets use the grid structure on a set of pixels in a critical way. And that's a geometry. We use it in design, and it's used in designing the neural net. But, you know, are there other geometries that one could use where one still insists on locality in the geometry of feature space that would be applicable and would give better performance? Now, in this case, the geometries might not be a priori. You see, when you've got images, the reason for the geometry is that's the way that the data is collected. It's collected kind of pixel-wise. But what if there is no a priori geometry? So what we found in our study was that there is a geometry, but it had to be found through a science experiment. That is to say, that Klein model that we discussed in the primary circles. So, so anyway, if we talk about a discovered geometry, we have discovered feature sets that carry geometry, primary circle, Klein model, etc. And we can use that to help design architectures, build that on top of the convolutional neural net to get something that works better. So, and in order to understand that, let me talk a bit about feature space modeling. So given a data matrix, you can also consider its transpose matrix. The rows of that transpose matrix are now the features of the data set. So when there are many features, it might be useful to create mapper models. And this compresses and recognizes correlations among the features. So each row of the original matrix now gives a function on the feature set and on the nodes of the topological model. So in fact, every data set in this way can be realized as a space of functions on, on graphs, actually, when I create these mapper models. And that actually is an important thing, because once I have a graph structure, there are things called topological signal processing, signal processing on graphs that gives you some structure on a set of functions rather than having it just be a flat set of vectors. So, and just to give you a sense of it, the microarray analysis of breast cancer, this was a study that we did a number of years ago with Monica Nicolau, effectively did this analysis. And it showed that the mapper model for the breast cancer in the so-called NKI data set looks like this. So that cohort A down there, it consists entirely of people who completely survived the full length of the study. Cohort B is poor prognosis. Cohort C is something intermediate. And so the question is, why? What's happening here? What's characterizing these different groups? So I've got these cohorts, but I can take the feature space, which in this case consists of 1,500 genes, and build a model of those. So I've got 1,500 features. There's too many for us to really wrap our heads around. But if I build a mapper model of it, I can start to wrap my head around it and get dimensionality reductions. And so what happens here is that you can see this graph for each of it's the same graph in all cases, but it's colored by the different cohorts. So just like I can color by an individual data point, I can also color by a cohort by taking averages. And you can see that cohort A and cohort B are vastly different here. So cohort A is blue on the bottom and red on top. Cohort B is red on the bottom and blue on top. And then cohort C is something that looks like a kind of a weaker version of cohort B. It looks quite distinct from cohort A. So it suggests there's something very special going on in cohort A. And indeed there is. Then there's a list of genes that describe that distinction. And similarly here, this is a study in the UCSD microbiome study. Larry Smarr is an investigator there at UCSD, and he studies the gut biome, which means the distribution or the bacterial populations in the gut biome of humans. And so those are the features, and in this case there were 10,000 of them, I believe, that we cut down on that feature space a bit to build these models of it. So you'll notice again the graphs are identical, but over here on the left, this is healthy people. On the right, it's ulcerative colitis. And you'll notice that they look pretty similar, except the ulcerative colitis has this red group, bright red group here, which you don't see over here. And similarly, there's Crohn's disease up here. Again, a lot of similarity between the two, but the Crohn's is missing the bright red thing up here. So it's it gives a very clean, simple way of analyzing, getting at what it is that's going on with the data by thinking of it as functions on the graph. And so that's what we want to do to now talk about a generalized convolutional neural net. So feed-forward structure is a set of objects like this, a set x naught through xn, and then correspondence. There are actually relations between these layers. So the xi's are called the layers. So when I have data like this, I can use this to create a directed graph. The nodes are the elements in all the xi's. Each xi is a layer. The correspondence determines the connections. So V is connected to W if and only if V comma W is in the ith relation. And so what you might do here is you might say, well, my relation is going to be, if I have a metric space or a graph, I'm only going to consider connections between nearby points. So things that are nearby or connected in the graph structure. So for example, if I take a discretization of the Klein model like this, that's what I can, this is what I can do. So I can build these local connections based on that Klein model's worth of features. So now if I take a neural network and I compute the Klein model's worth of features in there, which by the way correspond to taking dot products against exemplars for the points in the Klein model. And again, I would discretize it in a particular way. So what I do is I take the product of that with the grid. And so for every data point, for every image and pixel, I have not only a pixel value, but then also a value that describes the context that that pixel is in. Namely, is it part of an edge? Is it part of a ridge? And create features that way that I can then feed to a neural network that I will have built by connecting up a pair, which is a pixel, together with a point in the Klein model with other pairs like that, but that they all have to be nearby. Okay, so these are what we would call topological neural nets. And I want to add in here, this is joint work with Effie Love and Vasilis Maroulis, and also, he's not in here, unfortunately, Ben Filipenko also is involved in this work. So here's what happened when we studied this, these networks on MNIST. And so what we wanted to do, we wanted to study the generalization question. So that is to say, suppose I take MNIST and I add some Gaussian noise to MNIST. Now, when I do that and I train an ordinary convolutional neural net on it, the learning that I get, the accuracy that I get is exhibited by that lower blue line there. In other words, the convolutional neural net doesn't allow you to get any kind of generalization going. And then by the way, so this is noisy MNIST training set. This is training on the noisy set and evaluating on the clean set. This one is training on the clean set and evaluating on the noisy one. And now these four things here are all different variants on the topological structure. So the purple and the red, are circular layers. So these use only the primary circle. The orange and the green come from Klein features. Now, what's interesting here is you might notice that it's tapering off. You get to a high accuracy, and then after training more, you lose. The point is that the accuracy is not just measured on the training set, but it's measured on a test set, and it's a well-known feature of neural networks and of deep learning that you do get overfitting that happens over time, and the accuracy measure includes a penalty for the overfitting. So that's a well-known thing, but you'll notice here that the learning goes very rapidly up here to a high level, and whereas the circle doesn't get there quite as rapidly. The circle too will eventually taper down, but anyway, and what you can see here is similarly up here, you have a similar phenomenon where you train on the clean data set and you get, somewhat the same. I would say here, though, you notice that there's a difference here that the Klein stays higher, exclusively. And a similar generalizability question would be to train on one data set, and evaluate on another, not just to create a different version of MNIST, but to take something which is captured by kind of maybe even a different technology. And so here, what you get is, this is SVHN to MNIST generalizability. So SVHN is a hard data set, and MNIST is a much easier one. And so here you get this generalization going on for all the Klein feature things there. That's the green, the blue, and the black. And then these two down here are versions of an ordinary convolutional neural net. And similarly here, now when we're going from MNIST to SVHN, which is a harder problem, MNIST being the simpler gadget, you'll see that there's nothing happening at the bottom here. The ordinary neural nets don't get anywhere on that, and our various variants get to a much better place here. In this case, I believe we ultimately got to 3.5 or so, or sorry, 35 to 40%. So much higher than that 22% that we reported before.
We have one question from the audience, namely, what do the abbreviations mean? KF, CF, null?
Yes, thank you. Klein features plus Klein layer. Okay, and the other is just Klein features. So one thing that you can do is you can take the neural net and not impose the architecture, but just use the features. And so those are the different. But anyway, KF is Klein features, and KOL is Klein zero layer, is what it means. And then NOL and means normal layers. And then there's a notion of pooled as well. There's, if you are familiar with this, pooling is a lowering of resolution or a downsampling. And this is another data set, kind of recapitulates what happens here. So what's interesting here is also to discuss the learning rate and the amount of learning that happens on on various amounts of data. One of the big problems with neural nets is that they require a lot of data to get to a good place. And so what you can observe here is that if you look at SVHN, for example, these Klein layers up here, they follow this curve right here. So what you'll notice is that, and here, this number here is the total number of images seen. So the data set in this case consists of 60,000 images. You train on 50,000 of them. And so what this is showing is that by training on only 10,000 of the 50,000, you already get to the same accuracy as you get to at the very end with the other methods. So the ability to shrink the amount of data that you need to learn is significant, and it also applies here to USPS, which is another data set of images. This is US Postal Service, and then MNIST is a simpler data set, so the effect is not as pronounced, but I think it's sort of illustrated here in the case of SVHN and USPS. And now, so video is a much harder problem. There's a lot of video data sets. One is from University of Central Florida. It's a data set of human actions, and one is attempting to classify it. So, it's like running or, maybe hitting a baseball. And again, what you can see here is that there's an analog of the Klein model here. What are the features for video? And if you think about it, what it should be, and what we just used without doing any statistical analysis, is that the feature set for video should be the tangent bundle to the Klein model, because video should be thought of as little paths, maybe as infinitesimal paths if I take patches in the Klein model space. And so I get a tangent direction there. And so we use that structure of that tangent bundle to identify certain features and a network here, combining it with a so-called 12-layer ResNet, which is a much more complicated network. And we get here, when you plug in the ordinary convolutional neural net, you have this orange one right here, which is shows you what the accuracy is after I've gone through a certain number of learning iterations. And you can see here that with this tangent bundle, it gets there much more rapidly. And what's interesting here is that we're training on exclusively on the data set. Mostly what people do is they actually train on much more data from outside, and use what's called transfer learning on here. That, of course, is an intensive procedure, and we want to say that, well, we can circumvent some of that by using these tangent bundle features. Okay, so to conclude then, and Gary Marcus was head of artificial intelligence at Uber, and is now running is back in academia, but also running a new company. The problems that he points to in what he would call a friendly, critique of deep learning is that, well, it's very data hungry. It has trouble working with prior knowledge. It has trouble with generalization and adversarial examples. And he would summarize that as saying it cannot be engineered. In other words, you cannot work with it in an iterative basis and hope to get improvements. That so far it's still a little bit scattershot and empirical. So the methods that I've discussed here kind of address these problems in a way, and we're working hard on developing them to make them even more powerful going forward. So with that, I will thank you and take your questions.
Thank you. So before we get to questions, I would ask everyone to unmute themselves and thank Gunnar for his wonderful talk. So given the large number of participants today, we figured that it would be a good idea for people to raise hands, and then we're gonna call on them so that it's going to be a little bit more organized.
Okay, so I'll stop sharing here.
That sounds good. So we have a first question. Go ahead, Kaushik.
Hi, Gunnar. Thanks for the talk. I was wondering if you have any adversarial examples that you mentioned where TDA plus ML does better.
Yeah, we haven't actually done, particular adversarial examples. We would kind of view, for example, the one where we dirtied up MNIST, that could be thought of as an adversarial process, but, fair enough. We have looked at some situations where there was some clustering at the end, but it's kind of, and where you could see that you can cluster away some of the adversarial examples using Mapper, but it wasn't part of this study. Oh, so there's one in the chat there. Let's see. Do you think generalizability can be related to the topology of one architecture being a covering space for the topology of another architecture? I think the question, if you're thinking of covering spaces in the sense of the circle or the real line covering the circle, I'm not so sure about that. I think that the question about if one thinks of a space equipped with a covering, the kind of a check construction, that might very well, be something that might be related to the quality of the computations. Yeah.
So then we have Moskowitz.
Hey, it's Ira Moskowitz. Can you hear me?
Yeah.
Good. What you said about the tangent bundle was interesting, but that's quite a leap of faith to me. Is there any sort of theory backing that? I was sort of taken by surprise by that. I'm very interested in it.
Yeah, no, so see, actually, so that is, you make a great point. And so, of course, we could do the following. We could say, well, we believe it's going to be the tangent bundle. So we're going to do a statistical analysis. We're going to work hard for a year. And ultimately, what we'll find is we'll find some stratification of the tangent bundle, which will show you what's happening. But what I would view it like this, I would say that, let me reverse it on you and say, let's take the leap of faith and let's see if it improves things. And it dramatically improves things. So, so that's in fact kind of evidence for it. And actually that's really a key point here. And if you go to Marcus's point about engineering, see, if you start to have some mathematical primitives that are involved in building these feature spaces and building these neural networks, all of a sudden you are led to natural experiments that you can try. Otherwise, you kind of have to try to do things, empirically and so forth. So I think, your point is, yes, it's a leap of faith. And I would say that's a strong suit. that's a strength of the matter, that it is a leap of faith, but it was a leap of faith that worked.
Okay, no, I like it. Thank you. Thank you.
Okay, so then we have more questions in the chat. So it seems that using topological knowledge to architect the neural network results in faster learning using less trainment data, but not a higher level final accuracy given enough test data. Is that right? And do you think it could lead to more accuracy?
Well, if you looked at the video, you can see that actually, that we were kind of way ahead even at the end of the analysis. Now, the neural networks, because they have so many parameters, they're often able to actually overfit at the very end. So you can get to often to a very high degree of accuracy, but often it's an accuracy that is it is not a generalizable accuracy. So I think the answer is that oftentimes, you will get to the same final accuracy, but your model won't be as good or as generalizable. But at least with the video, it looks like it did lead to more accuracy even at the end. And maybe that end isn't at infinity, but it's sort of as far as we were able to go.
And then it's maybe if you could share the slides again, it says in the last graph comparing the two 12-layer networks, what did the ML stand for?
Okay, I'm not sure. Let's see. So share. Okay. Whoops. Okay. Sorry, I have to pull up my PowerPoint slides again. Okay. You mean the MF?
Ah, yes, then the MF.
MF, yeah. Oh my goodness. I forget. It was just the name that we attached to this. To this. I guess it's motion. Maybe. No, sorry. I think it's motion features.
Okay, very good. And then we have another question in the chat window. Rather than the topology of the models, architecture and such, one can represent the topology of the input directly as a feature of the model via an explicit representation in the optimization function. Do you have any thoughts on this approach?
Okay, let me, actually, can I?
Yes, you can also read.
I'm trying to see it here, the question. Do you think?
Well, I can.
Let's see. Oh, rather than topology of models, one can represent the topology input directly as a feature of the model by an explicit representation in the optimization function. Okay. Actually, I mean, I think that is a separate perpendicular direction that one could think about. I think it's, in general, the idea of getting these nonlinear constrained spaces in there and sort of studying them is important. So I wouldn't argue that what I'm talking about is the unique way of imposing topology in here. There are many ways. We have work on a topological layer, a topology layer to be put into the neural network. So this is not a unique thing. So I would say certainly that's what you describe as a possibility. Yeah.
And then there is another question in the chat window. Is it? Yeah, maybe you also want to take a look at it.
I see it. Sure, one could imagine that in other applications. So one thing that we're kind of looking at is, you might think about spectroscopy, for example, which is, a 3D, effectively amount to a 3D imaging where you actually have a 2D image for every frequency. And in those situations, maybe it's the case that edges and lines aren't important. Maybe it's something else. But we haven't really seen anything like that. And so far, we kind of feel like in all image applications that we've seen, the ability to capture at least edges and lines is really important. And what I would say is that, in fact, things that are important beyond that are kind of recognizing textures of various kinds. And even the textures can be gotten, so work that Jose Perea did for his Stanford thesis showed that you can build features for textures as Klein distributions or functions on a Klein bottle. So anyway, the answer is absolutely yes. What you're asking could happen. We haven't seen it yet.
Any further questions? Okay, so if there are no further questions for now, I'm gonna stop the recording. So, okay, we do have one question after all.
Yeah, hi. Hi, hello. I am interested in the natural image data set. So I was wondering, so you said that the distribution of 3x3 patches lives in a space that is like homotopy equivalent to the Klein bottle. So I was wondering, for example, if we take one picture from the CFR10 dataset and we sample 3x3 patches from this image, then it will have a distribution on this Klein bottle space. And if we take another image from this CFR10 dataset and sample the 3x3 patches, it will probably have another distribution on, inside this Klein bottle space. So I was wondering if there was a like a way to describe this kind of distribution of those 3x3 patches in the Klein bottle. like currently for me, I think maybe we can try to use persistent homology, like to find the description for the space of 3 by 3 patches for each single image. But then it's like a little bit hard for me to find the connection between the persistent homology result on a single image and those like structure in the distribution.
Well, let me say what you propose is something one might think of doing, because for some of these textures, what happens to show up is maybe you have different optima or different max values on the Klein bottle. Yeah. And so if you did persistent homology with respect to that function, you might see that and you might use it. I think it's an interesting idea, and one could certainly try to bring it to bear. And I would advocate for thinking in particular about not so much CFAR, but as for texture data sets. Yeah.
Okay. Also, I think it's like quite interesting that in the weight space of the convolutional neural network, we again find this like primary circle of the linear gradient, and yeah. I mean. I can understand that in the natural image data set, we have this linear gradient and quadratic gradient that has the most, like the highest density of those 3 by 3 patches. But then, like, why in this MNIST data set or C510 data set, like in the weight space of the convolutional neural layers, we again can find this like primary circle of linear gradient? Is this some like kind of coincidence?
Yeah, well, coincidence. I mean, I think it really is interesting that it happened. I think it's sort of saying that there's really something fundamental in the images that's driving both. I'm not sure I got the rest of your question there, but I do think it was fantastically interesting. Yeah.
Thanks a lot.
Okay, thank you.
So they're asking the citation for the paper. So the work is up under Topological Deep Learning, I think it's called, and it's on arXiv. So if you look me up on arXiv, you'll find it.
Perfect. Yeah, so we're going to wrap up, at least now, with the recording. Gunnar, thanks again for the wonderful talk. And I'm going to stop the recording, and then all questions can continue. The discussion can continue offline.
Okay, I have a hard stop at 9, so.
Okay, yes.
Okay.